Okay guys, in the previous video we did talk about the introduction on vector a little bit, on how it might be related to this topic, which is eigenvalue and eigenvector. So let's go back to our subtopic of a metric, which is eigenvalues and eigenvector. So what is it actually, right? So in eigenvalue and eigenvector, okay, just like its name, the mission is to find the eigenvector and later eigenvalue. So why do we need to find that value? Why do we need to find that vector? So basically, we want to determine which eigenvector that when being multiplied will give us, just like I said before, will give us just the expansion of the line, or maybe shorten the line, but not the other, not changing direction to different degree, different diagonal, right? So just look at this, right? Let's try to be clear out graphically after this. Okay, previously what we did is we multiply, right? We multiply a vector, right? So previously we have 1 1, let's say, right? And we multiply with 5. That give us 5 5. And we know that based on the graph, we're able to see that it is actually expanding the line, right? From 1 1 to 5 5, it is actually expanding the line, right? So that is, it is just one value, one constant value. Then we're able to just multiply and find the value, and if we look at it graphically, we'll know that 5 5 is along this line. So if you look at it graphically, so for the case of metric, okay, we don't have only one value. Instead, we have a set of variables like this. Okay, so we want to know which vector that when being multiplied will give us another value, another vector value that is on the same line, right? So basically we want to find the eigenvector and later the eigenvalue that when being multiplied with our matrix will give us a new vector that is on the same line, right? Maybe the line will be expanded, maybe it will be shortened, right? So that is the idea, right? Let's try to look at it graphically. Let's say we are looking at 1 1. Okay, let's say we want to find the vector that when we multiply will just expand the line, but not rotating the line, right? Basically, I want when I multiply this to 1 1, right? 1 1. Okay, and let's just try to multiply, right? So when I multiply with 1 1, it will give me -3 9. Now I need to make sure that if this is the metric, if this is the eigenvector for this one, it should later, right, this destination, this location should be straight up ahead, within on the same line, right? So let's see what actually happened when I multiply this, right? The line will expanding, of course, but where does it expand it to? Okay, so basically this is where negative 3, 9 is. So basically this is the original line. When I multiply my metric to this vector, it gives me this line, which is not along the same line. So this should not be the eigenvector for this metric. Okay, I hope you get the idea. We want to find out a vector that when being multiplied with our metric will actually just expanding this line straight up ahead. Right, not the line that is actually tilt like this, rotating, right? So maybe we can try with maybe another metric, another vector. Maybe let's try on 1, 2. So if we try on vector 1, 2, let's see what happened. So I multiply my metric with 1, 2, which is this line. Okay, I multiply it with the same metric, and it gives me this line. So basically, it is expanding, but it is actually rotating. It is not on the same line. So this is not a metric. I want a metric that just when I multiply it will just expand the line without rotating the line. So this is not it. Right? Let's just try several more. Let's say for the line maybe 2, 1. If I multiply with my metric, will it give me a line that is just straight up ahead, or maybe it will rotate to the other way? Okay. So when I multiply it, it gives me this line. Now it rotates far to my left. So basically this is not it. Alright, so let's try another one. Let's say 2, 3, and try to multiply it with the metric. What should you get? So graphically, this is where the line is. So again, not on the same line. It is actually rotating, not the one that we look at. Okay, so let's move to the other one, which is 1, 4. Okay, so let's look at this one and try to multiply it with this metric. Negative 6, 3, 4, 5. What should you get? So when I look at it graphically, this is how it looks like. It expands in the same line. So basically we can say that 1, 4 is the eigenvector. 1, 4 is the eigenvector for this one, for this metric. And when we have found out the eigenvector, later we can look for the eigenvalue. But that aside, I just want to show first the idea of what does eigenvector and eigenvalue mean. Eigenvalue is just actually the length of this line, right? We'll look at it later, but I just want you to understand what will you look at later. Right? So basically you can expect that you are going to be given a set of metric. You are going to give given a metric, and we are going to find out what is the eigenvector that when we multiply with that metric will give us an expansion of line along the original line. They will not be rotated, right? So that is the basic idea of what is going to happen in finding eigenvector and eigenvalue. Now let's talk about the formula. As you can see here, this is the notation that I use to multiply between a constant with a vector. Okay, a constant with a vector, and this is the notation that I use to multiply metric with a vector. Alright, the difference between these two is just that this is this vector being multiplied with a constant, one value. As for the case of metric, we don't have one value, but we do have a matrix. But the thing, right, actually the same. Right, so you want to multiply and get a new vector that is along the same line. So what we can say is we want to find the matrix multiplied with a vector that have the same result of a constant, which is denoted as lambda, multiplied with a vector. So we want it to be the same. Okay, for our case later we will know the matrix, but we will need to figure out this x and lambda. The x here will stand for the eigenvector, and lambda here will stand for eigenvalue. Alright, so if we try to simplify it even further, okay, we move this to the left hand side, so that will give us ax minus lambda x equal to 0. And if you simplify it, you should get a minus lambda x equal to 0. Right? But please note that this a here is in a form of metric. As for this lambda, it is actually just a constant, which is it is not comparable. We cannot really conduct any operation because they have a different form. So to make sure that this is also in a metric form, we are going to multiply it with identity, which later we'll change this into a form of metric that is equivalent to a. Alright, so another thing, okay, because of these two is the same, right? This should be the same as this, right? That's why it is equal there. Meaning later, in one properties of matrix, we can say that when you subtract, when you try to do it like this and you subtract between a and lambda, right? It is not invisible. Right, the metric resulted from this operation cannot be inverse. Simply said, cannot be inverse. So when we say that they cannot be inverse, one of the properties of a matrix that cannot be inverse is that the determinant, right? The determinant, I just put like this, the notation for determinant should be equal to 0. Right? The determinant should be equal to 0. So this is the basic idea you need to know first before we can proceed in calculating eigenvector and eigenvalue. Right? So we are going to use this formula, and we are going to also use this idea. Right? So we are going to discuss about that further in our next video. Thank you.